All right, welcome back from the break, everyone. Looks like we're going to jump right back into a little bit more performance discussion with Sam and peering speed improvements. Take our way, Sam.
All right. This is another one which showed up in the last session, which hasn't seen much movement yet. The basic observation is that while we're stuck with a certain amount of latency when map changes happen due to our consistency model, we're probably stuck with somewhat less than we currently have. So let's talk a little bit about the actual peering process. So when a new primary discovers that it is primary at the beginning of peering, what it does is it sends a request for the info from every OSD in the acting set, the upset, and then every acting set OSD which is not marked as down from every acting set back to the last time it knows that the placement group went active. This ensures that we see at least one info from every interval which could have seen a write, and that allows us to be sure about the most recent write version. After that, we take that info and figure out which OSD we're going to deem as having the authoritative log, and then we set it a log request to get the authoritative log. We use that log to update our own missing set. If it has new entries that we don't have, we take those entries, mark those objects as missing, so that later during recovery we can pull the most recent copy, and so that if we get a read on those objects before that point, we know to delay it. And then we send that log and request updated missing sets from everyone in the acting set, because for the same reason, we need to know which objects are degraded, that is, which objects have replica copies that are out of date, because we can't accept writes on those until we've finished recovery, and we need to know which objects are degraded generally so we can perform recovery. So if we're counting round trips, that's 1, 2, 3 before we even get to start, and this is before we even get to start performing I/O on the PG. And some of these are not totally necessary. For one thing, if we were primary before, but that is at the beginning of this interval, we find out that we're primary, because usually it's very the way it's currently structured, it's very stateless. We don't remember that we were primary before. We wipe all of our in-memory state and keep going and start over, because it's much simpler. But if we happen to be primary before, then we threw away a perfectly good set of infos that was totally up to date for the previous acting set of OSDs. Furthermore, we know that our own log is authoritative. So in that case, we could easily skip the first and second step and move right to get missing. And in the case that, in the fairly common case that an OSD that went down, one of the two replicas that is, or a down OSD came back up and we remained the same primary, which would be about 2/3 of the OSDs affected, or about 2/3 of the placement groups affected by rebooting a node, then those 2/3 of the placement groups would only need to do one round trip, enough to tell the other replicas that it's safe to go active again. So that's probably the smallest change we can make, and it shouldn't be too difficult. The second thing we can do is that we have a lot of information about the previous history, and there's a decent chance that based on the history, we can just guess that the previous interval has the correct, that anyone in the previous interval probably has a sufficiently up-to-date log. In that case, we could preemptively request the log and the missing from the OSDs in the most recent interval. That would allow us, in the case where even if the primary was the one that went down, one of the replicas would, on the first round trip, get the authoritative log, or rather get the log and missing from its replicas and be able to immediately send back the activation message, bringing us down to 2 round trips in that case. Let's see. Another wrinkle is that we can't actually do any, so before we're able to send the info back to the primary, as a replica that is, we need to flush all of our in-memory state to disk, because we can't report back that we have version 4000 until we've actually committed the operations that results in that version. So we can't send back our volatile in-memory knowledge that the most recent outstanding IO is 4000 until we flush it. We can't do anything about that, but we can probably relax the restriction to a commit rather than requiring it to be applied to the file system, which on XFS at least happens after. Doing that would allow us, and to do that, all we need to do is track objects that are unstable on a particular replica across interval boundaries, which we need to do anyway for replicas. So that may not be too bad. I'm not sure how big a win that one will be, since you can only have a certain number of uncommitted file store transactions before the journal starts to throttle. But I think the one where the primary simply doesn't forget its cached infos across an interval is probably the biggest one. All right, any comments? I've got I generated if you look at the blueprint, I generated a PNG with the current PG state diagram, if you'd like a little more information. The area I was talking about is the peering box under the primary box, under the started box, under the recovery machine box. And I was talking about the get info, get log, and get missing states. Questions? You guys have been able to hear me this whole time, right?
That was really fast.
Yes. Yes, we have.
Do you want me to try that again, but slower?
Actually, I think
Sam,
we just wait until the allotted time my brain might catch up.
Okay.
Sam, remind me again at the very beginning of this, how often does this happen? Is this on map update, or is this on when?
It's on any map update that changes the acting set, the upset, or the primary for a particular placement group. So all of the OSDs paying attention to a particular placement group for that particular placement group will go through this process when the acting, the upset, or the primary change.
Okay.
So if you mark an OSD down, that OSD is probably in about 100 placement groups. So about 300 OSDs will have like one placement group go through this process.
Okay.
Out of their 100 stored.
When this happens, is there a cascading effect on like the monitor in terms of needing to grab specific versions of the new map, or is it?
No, that part's gossiped, and the OSDs store local copies of all of the old OSD maps.
Okay.
So there is work to be done on the monitor, specifically in a slower path version of what I just described can be derisively referred to as the fast path. There's a slower path where the current primary or current acting set is not appropriate, perhaps because the new primary has no data whatsoever on this placement group. In that case, the primary will send a request to the monitors requesting a different acting set. This is the PG temp mapping, which will cause the placement group to be temporarily remapped. And then, because that changes the acting set, we go through another interval change. But the new primary, when he looks at the temporary acting set, will come to the conclusion that it's fine and proceed with pairing.
Fun.
That one is going to be harder to optimize. Although I think there actually is already logic in the monitor now that when you do something that there are heuristics in the monitor that will cause it to preemptively create those temporary mappings in a lot of cases. I think that went in before Hammer. So that does help that case somewhat.
That does ring a bell.
Joao would know more about that. But yeah, I think that actually did go in. Basically, when you do certain administrative actions, the monitor will spend a bounded amount of time trying to figure out what the implications are and building up a partial temporary mapping. That should reduce the amount of effort the OSDs have to go through. And then whatever they don't get to, then, okay, the OSDs send them a temporary update request anyway. Is that right, Joao? Maybe? Okay.
That's it. There's Joao. I saw Joao.
Okay. I was trying to say that PG temp thingy does ring a bell. I do think the logic is there, or at least a bunch of logic regarding PG temps. But anyway, that's all. But whenever you wish to actually take a look at this, just let me know and I will
Yep.
look, basically.
That part's actually parallel, so that's a separate optimization that we can do, and I think we already at least partially did. But the part we need to do on the OSD side is simply make it more clever about this process, especially leveraging information that it already has that we currently throw out. I think getting 2/3 of a size 3 pool to appear in one round trip would be pretty good. So it needs to be at least one round trip because we need to notify the replicas about some state information. Specifically, I mentioned before that we go back to the last interval where we could possibly have, where we know we went active. And the reason we know that is that every placement group records a monotonically increasing epoch number that records the most recent interval it has heard of the placement group going active in. So before we go active, we need to make absolutely certain that every replica in that acting set persists that number before we begin accepting writes. So that's there needs to be at least one round trip for correctness reasons.
How tough will it be to do this, Sam?
The primary version, I don't think it's going to be all that hard. What bugs me about this is that the current design is, for some version of the word, simple. And it's already hard to read. And this is going to make it harder to read because there will be ways to bypass some steps that you currently always see in the debug logs, which is going to be annoying. And it'll increase the number of ways bugs can propagate from interval to interval. Because right now we throw out a lot of information, so just marking an OSD and a placement group down is usually enough to bypass a bug if it was in ephemeral state in the PG primary, or replicas for that matter. But this way, a lot of state's going to leak through to another interval, so it'll be harder to get rid of it. Not that hard though. Huh?
I was just gonna say this is gonna have to be documented really well.
I mean, yeah. The problem is after a while, the algorithm itself really isn't that much less complicated than the code at this point. It's not that the code is hard to read, it's just that the peering algorithm, there's a lot to it.
Yeah. Do we have the current peering algorithm documented?
Yeah, well, I mean, there's words in OSD internals peering, and then I have a Perl or a Python script that will read the .cc files and generate the state diagram, which is kind of useful. But
nice. Okay.
The simplest way to understand it is really just to read the code. It's implemented as a boost state chart, so the states are like entities in the code that you can actually see.
Sure. Okay.
Yeah. And usually when you're looking for a bug, you're looking for a divergence between the algorithm and the code anyway. So just reading the documentation will let you find it.
Okay, so the goal right now is to go from essentially like, what did you say, potentially four round trips, 5 round trips down to 1?
Well, so in the worst case, we have to do all of this. Because if the relevant logs are actually 4 intervals back, because we're in some situation where some rack was flapping up and down and caused a few hundred maps of just complete insanity to happen, then we actually do have to talk to all of the OSDs involved because we really have no clue which one has the right information. The idea here is to take the simple common cases where nothing interesting or exciting happened. All that happened was someone rebooted a node, and therefore a map marked an OSD down, and then some short period of time back up. To simply take that case, exploit information we already have, and complete it faster.
Sure. Okay.
So the slow path will still have to be slow, but at least this will make the common cases faster. People just complain a lot about the I/O impact of restarting an OSD, so this will help with that somewhat. Well, probably a fair amount. Actually. it's unclear to me how much of that is the actual is the message round trips and how much of it is two commits are needed to complete this process. There's a commit at the beginning before you can talk to the primary again, because you can't communicate any of your in-memory state until it's been committed. So you have to complete that before you can respond to the first message. And then before you can begin accepting I/O, you have to commit the second number that is the last epoch started number. And both of those seem to be pretty much necessary. So if those are the overriding requirement that if those are the part that are actually causing most of the problems, then something else will be needed. But we can do this at least. We'll see.
Okay.
It'll also reduce load somewhat during peering because you'll have to handle fewer messages. Any questions?
Are there other more difficult optimizations you haven't put in this Etherpad that you've thought about already?
I think this is kind of it. Like I said, so we could always just request. I mean, okay. So if we wanted to be sure that we never had to do the get log step, we could always request the log and the missing from all of the replicas every time, and that would work. It would just increase the amount that we had to send over the wire. So I don't know if that's. I mean, for all I know, wasting that bandwidth is well worth it to avoid the round trip. That would get us in the worst case down to 2 round trips, I believe. But the logs are pretty big. In the case that it would actually help, it's probably the case that we've been unhealthy for a while. So we're probably closer to the 10,000 log entry bound than the 3,000 log entry bound. And at, some number of kilobytes per log entry, let's say 1 or 2, that's whatever 1 or 2 kilobytes times 10,000 is. It's actually quite a lot. That may not be worth it. We'll have to see. I'm not sure that with this peering algorithm, there's a lot you can do to get better than that. It seems like you definitely need to.
Could you preemptively share more of this information before peering starts?
No, because peering starts as soon as the replicas don't actually wait for that initial request. That initial get info usually gets sent twice. It gets sent preemptively by the replica as soon as it sees that the interval changed. And then it receives a request from the primary saying, please send this. And the reason is that the primary doesn't really know that the replica has a copy of the placement group. So it needs to get a null answer if the placement group doesn't have it, or if the OSD doesn't have it. But it occurs to me that I fibbed a little bit. It's not necessarily the case that we need to commit the previous interval's writes before we can send the response and get info, as long as the primary is really careful not to remember any of that information if the OSD goes down. But that would be hard and error prone, but possible, because we do another commit before we actually begin accepting. Actually, no, the primary accepts reads before that point. We don't block reads on. Yeah, it may not be much of a win. We'll have to see. The problem is that you really do have to complete. Let me think. You really do have to have the previous interval's writes committed before you can accept reads, because otherwise you might allow a client to read state that later turns out to be divergent. So you can't read recent log or objects modified by recent log entries until you're sure the other replicas have committed the log.
Right.
In which case we might be able to bypass the first commit. Possibly. We'll have to think about that.
If we, outside of this peering algorithm in particular, have we measured the general latency of peering overall, and whether it's like impacted more by this algorithm being slow, or just being serialized based on individual PGs doing more work.
The serialized based on individual PGs doing more work is this algorithm. This is all it's doing during that time. Everything else was blocked behind it. There isn't anything else the PG can do until this completes.
Okay.
Is that what you meant?
Yeah, but are they all operating independently at this point in their own thread pools, or they're operating per shard? Like, could we increase the concurrency in which they're peering?
I mean,
PGs
possibly,
to help things out?
but I don't think that's the main problem. That part's already pretty well parallelized, and these are the peering process has a much higher priority than client I/O.
Okay.
And that it happens in its own thread pool. It's different. The closest thing there is to a bottleneck is that the messages come in through the regular dispatch process, not the fast dispatch process. So they are serialized on the OSD lock, but there are far fewer peering messages than there are client messages. And I've never seen any evidence that were serialized there.
Mm-hmm.
I mean, you only have 100 PGs per OSD or something. You don't have thousands. So I don't think that's likely to be a problem. Although I don't know, erasure coded pools mean you handle a lot more messages per PG than with a replicated pool. So maybe. Yeah, something
It seems like it's worth measuring at some point.
Yeah, I still suspect that in a sort of hierarchy of needs, cutting down round trips is going to be more valuable than anything else.
Mm-hmm.
Just means we're going through. If there is serialization, we serialize less.
Yeah.
All right, that's all I've got.
All right. A few minutes left. That's all right.